Last day we taught you a method of solving one-dimensional kinematics problems without your brain, just following a recipe. And I made that claim not in jest. A computer program can solve these, and a computer doesn't have a brain. It just follows a recipe. And so let's follow that recipe and solve a couple of problems. Make sure everyone knows how to do it. You're going to have at least 2 of these on the midterm. A soccer player running at a speed of 2.6 meters per second decides to accelerate. For the next 18 meters, he speeds up with an acceleration of 0.45 meters per second every second. What is the speed at the end of the run? With your neighbor, see if you can crack that problem. The equations are at page 21 of your textbook. I'll put them on the board here. Okay, let's work this one together to remind you. The first thing we do is turn off our brain, and then we just find 3 of these 5 variables from the problem statement. Well, originally that soccer player is traveling at 2.6 meters per second. He then speeds up with an acceleration of 0.45 meters per second, and if I call this a positive velocity, in order to speed up I have to have a positive acceleration. They have to be in the same direction. We are told that he has that acceleration for a distance of 18 meters. Now, the next step of our recipe, we have 2 blanks. One of them worth $1 million in a houseboat, one of them worth nothing. In this case, we're asked for the final velocity. That makes the time interval the who cares. Well, that who cares is actually the piece that tells me which of the 4 equations is going to solve my problem. If I don't know delta t, and I don't want to know delta t, I'm looking for an equation that doesn't have delta t in it. Well, there's a delta t, there's a delta t, there's a delta t. It's this last equation that I want to use. Now remember, I told you last day, these equations will be on the front page of your midterm. This table will not. Okay? But we didn't use the table, we just looked for delta t's. And we found that we needed to use this equation. V final squared is equal to V initial squared plus 2a delta x. V final squared is going to be 2.6 squared plus 2 times 0.45 times 18. That gives me V final squared is equal to 23. And, is that right? Yes, 23. And that gives me a V final that's equal to 4.8 meters per second. Okay, notice how my brain was turned off during that whole process. Okay, let's try another one. This time I'll give you enough time to solve it yourself. The length of the barrel of a primitive blowgun is 1.6 meters. Upon leaving the barrel, a dart has a speed of 24 meters per second. Assuming the dart is uniformly accelerated, meaning we can use these kinematic equations, how many seconds on your Mickey does it take for the dart to travel through the length of the barrel? So, with your neighbor, go through that recipe. Yes, sir?
We're assuming that the initial is 0?
Oh, are we?
Yes.
Yeah. Yeah. Good point. Because there's only two numbers in that problem. Sometimes you have to read between the lines to get your third piece of information. It has to start from rest. How many of you are sitting next to a neighbor who has an answer? Raise your hand. Good. Okay, let's go over it. We know that the dart travels a distance of 1.6 meters, and it starts from rest, and it has a final velocity of 24 meters per second. That leaves two empty spaces, one of which is worth an A in the class and a chance to go to medical school. The other one we don't care about. In this problem, we're asked for the time. That makes the acceleration the who cares. That who cares tells me which equation is going to give me my answer. I go to my list and I look for the equation that does not have acceleration in it. Well, there's acceleration, there's acceleration, there's acceleration. I have to use this second equation here, which is the operational definition of average velocity. So I write down the equation. I plug in what I know. This is 1.6 is equal to 1/2 0 plus 24 times delta t. Well, 0 plus 24 is 24, half of that is 12, so that gives me a delta t of 1.6 over 12, or 0.133 seconds. See if your neighbor got that answer. If not, you know what to do. Okay? Okay, now let's turn our attention to the topic of today's lecture, gravitational acceleration. I have a skier going down an incline, and we're asked which of these vectors, A, B, C, or D, best represents the direction of the skier's actual acceleration. Okay, is it A, B, C, or D? With your clicker, please. Okay, last call. Whoa. Well, it's either C or it's D. C or D. Probably not B. Okay? Now, the answer, of course, is C. We've known that since the first tutorial. If we look at the velocity of that skier, it's down the ramp. And as she goes down the ramp, she speeds up, so the vector gets longer. The change in velocity is what I have to add to that short vector down the ramp to get a long vector down the ramp. And there's the plus sign right there when I stack them head to tail. Now the acceleration has to, every stinking time has to be in the same direction as the change in velocity. Now, those of you, and there were a lot of you that chose D, I would ask, what were you thinking? And I'll tell you what you were thinking. Gravity. Right? Right? And if I had asked you to put a number to that vector, what would it have been? 9.8. 9.8. Because some of you have had high school physics, and in that physics class, the teacher may have said something like, everything on planet Earth has acceleration 9.8 meters per second down. Right? Right? I know this is true because during the summer, I teach courses for high school physics teachers. They come from all over the country. During one of those classes, I was working with them on this ball up the ramp activity, and this is a quote from one of the students, one of the high school teachers. A question I have is, could you draw the acceleration vectors straight down? Because that's the way they really are. Or do I have to put them down the ramp like your tutorial says? You know, this drives me crazy. This idea that everything has acceleration 9.8 meters per second. My velocity right now is 0. If I wait a second, it's still 0. I haven't changed it. My acceleration right now is 0. And yet some may say, well, Greg, you're going in a great big circle as the Earth turns. Yes, I am. I'm going in a big circle every 24 hours. And that is an acceleration. We'll talk about that acceleration in a couple of weeks. If I calculate that acceleration due to my going in a circle, it turns out it's 0.00005 meters per second. It's negligible. It's 0. Okay? My acceleration is 0. Now, I'm worked up about this because, well, let me explain. Before I was teaching classes here, I would go to Seattle every summer, and I was the director of the Summer Teaching Institute for Lillian McDermott's research group. And she would bring large groups of teachers from all over the world. And that program was very intense. It was like 8 hours of tutorial each day. Think about that. 8 hours of tutorial each day. So by Friday, my students, my teachers, were getting kind of fried. And I sensed that they were about to melt down. So I said, folks, we're all teachers. We've got a lot of experience teaching. Let's just take a break. For the next couple of hours, let's just share with each other our most memorable teaching experiences. Who wants to go first? And this old gentleman, he was waving his hands. He was so excited. And he just got up in front of that group and he said, I was teaching my class about gravity. And I went to my best student and I pointed at his heavy book and I said, what's the acceleration of that book? The student said 0. Well, I can only imagine. It was his best student. He looked at the book, not moving. Wait a second, it's still not moving. He said 0. So this old man, he says, so I had him come up to the front of the class, and I had him hold out his hand, and I put the heavy book on his hand. And I said, okay, now, tell me, what's the acceleration of that book? I can only imagine it's his best student. It's not moving. Wait a second, it's not moving. He said 0. And then this old curmudgeon said, I made him stand in front of that class with his arm out there with the heavy book until he could tell me that the acceleration of that book was 9.8 meters per second per second. He was just proud. He was just beaming. And I was in the back of the room with tears running down my face trying to calculate how many thousands of students this old man had ruined. I mean, first do no harm. I mean, some of these teachers need to be put down. I didn't mean put down. I just meant taken out of the teaching profession. Okay. Now, when does something have an acceleration of 9.8 meters per second per second? Down. Free fall. Free fall. Folks, this definition of acceleration, the change in velocity over change in time, that will always work. That will always give you the right answer. That's why we call it a definition. That definition happens to give us 9.8 every time we have something falling off the physics building in a vacuum. Okay? In those cases when something is falling near the surface of Earth in a vacuum, we get 9.8. Whether it's a grand piano, whether it's Greg, whether it's a BB. Now folks, I'm going to pause here for a moment. We're going to talk more about significant figures on Friday. But for now, I just want to point out that 9.8 is, well, really close to 10. And it turns out that if we use 10 instead of 9.8, the numbers work out so much easier, and we can concentrate on learning the physics instead of trying to figure out what 3 times 9.8 is. Okay? Now, how many of you are planning to take the MCAT and become doctors? Raise your hand. Okay. On the MCAT, they do not use 10, they use 9.8. And that means that those of you that want to be doctors, when you're doing your homework, when you're doing the exam, and when you're taking the MCAT, I want you to use 10. Because it's going to be so much easier than 9.8. The MCAT is a multiple choice test. You're going to get your answers so much faster than those other people, and one of your answer is going to be so close to one of the possible solutions, you'll know it's the right thing to do. The other people will end up serving fries at McDonald's, and you'll get to be the doctor. Okay? Now, that was the goal. So 10 is what we're going to use. Now, how many of you have been to the Leaning Tower of Pisa? Anybody? Were they letting people up in it? Okay, so you got to go up to the top there?
I didn't.
Oh, you didn't? Okay, I went when I was 8 years old. My dad was stationed in Germany, and we visited there. And I was a little nervous about going up in that Leaning Tower. Fortunately, my dad was just cheap enough that there was no way he was going to pay to take a bunch of kids up there. So I didn't have to go. Now, you all know the famous story that Galileo, the great scientist, is supposed to have gone up there with 2 rocks, one little rock, one big rock, and dropped them, and they land at the same time. Now, scientists don't think that Galileo actually did that experiment. I'll explain why in a moment. But we can do that experiment here, only we're going to do it with a rubber ball and a feather, and you'll see that they drop at exactly the same rate. Okay, you want to see that again? Okay. At exactly the same rate. Now, clearly what's going on here is that there's air resistance that's slowing down the feather. So we're going to get rid of that air resistance by pumping the air out of here. That's going to take a little bit of time. So why don't you get to know your neighbor? Find out what they are going to do this weekend. I pumped out the air, and now we'll do this race again, and we see that they land at the same time. Did they, you people in the front?
Yeah. Oh yeah.
Oh yeah, oh yeah, thank you. Okay, just about. If we're worried about that just about, we can make a better vacuum by going to outer space. Now, people, if you were homeschooled and if your parents taught you that we never went to the moon, that instead it was all done at a movie theater studio, just ignore this part, okay? Don't doubt your parents. But we left stuff there. It's still up there. Just saying.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that?
How about that? I love that. He sounds so surprised. Whoa, it worked. Who knew? Okay. Now I suggested that Galileo didn't actually climb the stairs of the Leaning Tower of Pisa, and that's because Galileo was famous for his thought experiments, his Gedanken experiments. And we have in his notes the description of one such Gedanken experiment. He suggested that if you took 3 identical rocks, and that's what rocks look like in Italy, very regular. If those rocks are identical, he argued, there's no reason to suspect that one would land first. They would all land at the same time. He then argued that if they're all going the same speed at the same time, putting 2 of them next to each other wouldn't change anything, that all still land at the same time. And then he argued that if a spider were to spin a web between those 2, or if we were to use super glue, they were moving next to each other anyway. They were always going to be side by side as they fell. What's the web going to hurt? Or what's the super glue going to hurt? And now we have a large rock and a small rock, and they land at exactly the same time. Because he did this thought experiment, he didn't have to climb those stairs. There was no reason to do the actual experiment and have to worry about someone. No, you know, I think the big rock landed a little first, you know, a little sooner. That's why we think he didn't do it. Now we're going to practice this idea with a little exercise, cliff diving. Oh, not that cliff. Do you even know who that is anymore? No. You ever watch Cheers, where everyone knows your name? Okay, it's a classic. You got to go back to Cheers. He's famous for telling his friends while they're sitting at the bar, women, can't live with them? Pass the beer nuts. Okay, I'm sorry. I went to high school on the island of Guam. It was a marvelous place. And the island of Guam is 32 miles long, and it varies from 4 to 8 miles wide, depending on where you are. And the interior of the island, away from the beaches, is just very, very dense jungle. And there are very few trails that are cut through that jungle. And if you follow those trails, you find all sorts of fun things, like tanks that were left there from the Second World War. What we would look for, my friends and I, were waterfalls. There were some of the most beautiful waterfalls in the interior. And below each of these waterfalls was a pool that was just wonderful to swim in. And we would always check the pool to make sure that it was deep enough. And then my friends and I would hike to the top of the cliff, to the top of the waterfall, and we would jump off. But before we jumped, we had a little ritual. Stone, and we would drop it. And all together we would count 1 1,000, 2 1,000, 3 1,000, until it splashed. And we had a rule. The rule was, if it went to 2 1,000, everyone had to jump, or you were a wussy. Okay? The rule also stated that if it went to 3 1,000, we all marched down the cliff, and no one speaks of this again. Okay? Let's see why this is a good rule. If I drop that pebble and it goes 1 1,000, 2 1,000, splash, how fast is it going right before it hits the water? 20 meters per second. That's what an acceleration of 9.8, call it 10 meters per second every second means. Every second that goes by, I take whatever that pebble has for velocity and I add 9.8, call it 10 meters per second down. So if it starts from rest, it speeds up the first second to 10, the second to 20. It's going about 40 miles per hour. Go ahead and jump. You'll be fine. Now, how high is that cliff if it's a 2 1,000 jump? Do I use the slowest speed of 0 or the fastest speed of 20? I use the average speed, halfway in between. On average, that pebble was dropping 10 meters each second for 2 seconds. You are 20 meters high. Go ahead and jump. Now let's suppose that we drop the pebble and it goes 1 1,000, 2 1,000, 3 1,000. How fast is the pebble going? How fast would you be going right before you hit the water? 30 meters per second is more than 60 miles an hour. That water is going to seem like concrete. I suggest you point your toes. Actually, I suggest you point anything you don't want to lose. Okay? Now, how high are you if it's a 3 1,000? I don't use the slowest speed of 0. I don't use the fastest speed of 30. I use the average halfway in between of 15. On average, this pebble is dropping 15 meters each second for 3 seconds. That's 45 meters. That's half a football field. Don't jump. That's crazy. I have 2 younger brothers, Kenny and David, who claim to have jumped a 3 1,000 cliff at Lake Powell. I didn't see it. I can't verify that they did it. But they're neither one of them quite right. It may have happened. It may have happened. Okay, let's look at this problem 15 that you voted off the island. This problem 15 involves a ball that is being dropped from rest, and it drops 2 meters. And in the first part of the problem, we're asked, how fast and in what direction is this ball traveling right before it hits the floor? Now, folks, this is a one-dimensional kinematics problem, motion problem, but it's also a free fall problem. As soon as you let go of the ball, nothing's touching the ball, and the only force on the ball is the gravitational force. Those are cases where the acceleration is 9.8, let's call it 10, meters per second down. I solved this problem by setting up my list of the 5 variables. Notice that because things are going up and down in this problem, I'm using y instead of x. It's no big deal. I usually use x when things go left and right, and y when they go up and down. Now, every morning when you wake up, you have a God-given right to choose your own coordinate system. You could choose up to be positive, you could choose up to be negative. It's your right. You do not, however, have a right to change your coordinate system in the middle of a problem. Once you choose your coordinate system, you stick with it through the whole problem. I'm going to choose up to be positive and down to be negative. In that coordinate system, my acceleration in free fall is negative 9.8, I'm going to call it negative 10 meters per second every second. Now, the minus sign simply means down. Down. Now, the initial velocity in this problem is 0. I need 3 pieces of information to proceed. The other piece of information is my delta y. Tell your neighbor really quick what delta y would be. Okay, if your neighbor said 2 meters, you've got to slap them for their own good. Okay? The displacement vector is a vector that goes from the very first starting place to the very last ending place as the crow flies. That's a vector pointing down. Its length is 2 meters, but it's down. Okay? In this coordinate system, that means a minus 2. Now, that leaves 2 blank spaces, V final and delta t. I'm looking for V final. That makes delta t the who cares. If I don't care about time, I use the kinematic equation that doesn't have time in it. Now, folks, you may have thought that I was just being picky about the minus 2 meters. Not so. If you had put plus 2 meters instead of minus 2 meters, you would be taking the square root of a negative number. If you do that, your calculator will explode. There will be shrapnel all over the room. You don't want to do that. Okay? That minus sign is critical. Now, when I take the square root of this positive number, there are two solutions. Either positive 6.3 meters per second or negative 6.3 meters per second. I chose the negative because the ball is still traveling downward right before it hits the floor. That minus sign, again, is important. In part B of this problem, we let the ball bounce and it rises up 1.5 meters. Now, it was going 6.3 meters right before it hit the ground. Is it reasonable to assume that it left the ground also going 6.3? Why not?
Because it doesn't go back up to 2 meters.
Yeah, if it was going 6.3 meters per second, it would go up 2 meters. It didn't. So it's got to be something slower than 6.3. Well, we can find out just by doing the same process over again. The first thing we put in this list is my acceleration. In this coordinate system, that's still negative 10. 9.8, call it 10. In this case, it's the final velocity that's 0, and the delta y in this case is positive because the ball is traveling upward. Again, that sign is critical. I'm looking for V initial. I don't care about time, so I use the same equation. But now it's V initial squared that I'm looking for, so I have to bring this stuff here to the other side of the equation. If I didn't have one of these negative and one positive, again, I'd be taking the square root of a negative number, and that would be a problem. Now here, the answers are a plus 5.5 meters per second or a minus 5.5 meters per second. Since it's traveling up, I chose the positive. Now part C, I suspect, is what got this thing booted off the island. Part C asks for the acceleration during the bounce. And that's going to be V final minus V initial over the time that it takes for the bounce. And by final and initial, I mean at the beginning of the bounce, the end of the bounce. And we're told that that bounce lasted for 0.02 seconds. Now, what's my final velocity? Well, by final, what I mean is this initial. At the end of the bounce, I'm at the beginning of the rise. And so this final is going to be plus 5.5 meters per second. My initial is at the beginning of the bounce. Well, that's going to be this final over here. The beginning of the bounce is the end of the fall. And so that's going to be negative. And here's where it's important to keep track of signs. I'm subtracting V final, and V final is negative 6.3. The minus minus gives me a plus. That's going to give me 11.8 over 0.02 seconds. And that's going to give me a positive 590 meters per second every second. That's a huge acceleration. Okay? That's, well, 59 times the gravitational acceleration, 59g. If that was you, you would be mush. Mush. Okay? Check that your neighbor followed that. Now, folks, I could also have solved this part C graphically if I used the operational definition that acceleration is just a change in velocity vector divided by the time. My initial velocity would be down 6.3 meters per second. Notice I don't put a minus sign there because I've got an arrow down and I'm just labeling that vector with its magnitude. That would be the initial. My final would be 5.5 meters per second up. Now the change vector, if I'm looking for a change, I put them tail to tail. And my change vector is what I have to add to my initial to get my final. That's my change. And that change has to be enough to, there's the plus sign right there. That change has to bring the initial up to 0 and out the other way. And so that is going to give me an acceleration of 11.8 meters per second up over 0.02 seconds. That's going to give me the same answer. Okay. Now, before I go any further, I just want to address something that I noticed as I was picking up your homework. Some of you, when working that problem where you throw the book up into the air, was it 15 meters per second? And it lands a distance 12 meters below, and you want to know how fast the book is going. That's the international symbol of motion. What's that final velocity? Some of you, I'm afraid, are making this way harder than it needs to be. Some of you are worried about how high it goes. And you calculate how high it goes, and then you drop it from rest from up there. You make this a much harder problem than you need to. It turns out all you need to do is go delta y, a, v initial, v final, delta t. If my coordinate system is up positive and down negative, this is going to be a negative 9.8, call it 10 meters per second squared. My initial velocity is going to be a positive because it's up 15 meters per second. My delta y is from the first starting point to the last ending place as the crow flies. That's my delta y. And that's going to be a negative 12 meters. I don't have to worry about this part of the motion. That's taken care of in the equations. Okay? You just have to know how different the final position is from the initial position. Okay, if you did it a different way, you'll still get the right answer, but it'll take you 3 times as long. Questions on that? Okay, I have a check question for you. It turns out you were listening to the radio and they had a contest. You called in and you had the right answer. You're the winner. The prize is a ride in a hot air balloon over Montana. Now, because it's Montana, they let you bring your rifle. And because it's Montana, they let you fire it straight down. There's no one down there. Okay? So there's your gun. I can't draw very well. So you fire the gun straight down, and the bullet leaves the barrel with a velocity of 350 meters per second. My check question is, what is the acceleration of the bullet at a time 0.01 seconds after it leaves the barrel? Okay, talk to your neighbor. What's the acceleration of the bullet 1/100th of a second after it leaves the barrel? Okay. Folks, some of you are doing calculations, and that means I tricked you. Once that bullet leaves the barrel, it has an acceleration of 9.8, let's call it 10, meters per second down. Okay? If we neglect air resistance. Now it turns out that with a bullet, to you hunters, neglecting air resistance is a silly thing to do. With a bullet, air resistance is one of the major factors in whether you're going to take home an elk or not. Okay? But in this class, we're never going to worry about that air resistance. We're always going to deal with cannonballs that are very massive. Or we're going to deal with things large enough that air resistance won't be an issue. In any case, you can always ignore the air resistance in the homework problems, on the exam problems. Okay? Now, what that means is that any time something is in free fall, it has acceleration 9.8 meters per second down. That means if you kick a football, as soon as it leaves your toe, it is in free fall. If you throw a baseball, as soon as it leaves your fingers, it is in free fall. Whether you throw it up, whether you throw it down, whether you throw it sideways, as soon as it leaves your fingers, it is in free fall. The acceleration is 9.8, call it 10 meters per second down. Here's a problem that I think really gets at whether you understand this idea of gravitational acceleration. You and a friend stand on the edge of a 40-meter cliff. You throw a red ball straight up at 30 meters per second. You've got a good arm. At the same time, your friend throws a blue ball straight down the cliff at the same speed. 2 questions. Which of those balls, the red one or the blue one, is going to be going fastest right before it hits the ground? Second of all, the red one is obviously going to hit the bottom of the cliff after the blue one. How many seconds after? With your neighbor. See if you can do that in your head. This is not something you would calculate. You would do it in your head. Okay, since we only have 2 minutes, I just noticed the time. Since we only have 2 minutes, let's do it together. You throw the ball straight up at 30 meters per second. 1 second later, how fast is it going, people? Shout it out. 20. That's what an acceleration of 9.8, call it 10 down, means. Every second that goes by, you take your velocity and you add 10 meters per second down. So it would be 20. A second after that, you take the 20 up and you add 10 down, you get 10 up. A second later, you take the 10 up, you add 10 down, you get 0. A second after that, you take 0 and add 10 down, you got 10. The second after that, you're going 20. The second after that, you're going 30. And that's the same speed that your friend threw the other ball, and that means that both of those balls will land at the same speed, but not the same time. The red ball is going to be landing 6 seconds later. That's all there is. Folks, we're out of time. We'll finish this on Friday.